Hello, this is Mrs. Schroeder. We're going to talk about stoichiometry involving gases. Now, if you remember stoichiometry, we have a way to bridge the gap in a chemical reaction to find out something about a product or a reactant based on what we're starting with or what we're ending with. The ideal gas law is a way for us to relate that gaseous amount to other variables like pressure and temperature and volume, which might be changing in the course of the reaction. So I'll put this cute little picture up here to remind you we have moles of A. In order to go from moles of A over to B, we have to go the ratio of B over A, and then we can get 2 moles of B, whatever that might be, whether it's a gas or a liquid that we use density for, or our solid that we're using our molar mass for. Somehow we can change this to anything we want once we get 2 moles. In this section again, chapter 12, we're going to do this last part right here, applying our knowledge of reaction stoichiometry to our gas laws, our ideal gas law. So often when we have a reaction in an industrial setting or even in a lab, we produce a gas. It's difficult to measure the mass of a gas because we can't really put it on a scale and weigh it. It would just float away. So often we capture it in a container of some kind and measure its volume, not its mass. We have to know the pressure and temperature that gas is under to be able to relate and figure out the moles. Again, engineers have to know how much gas is produced so that we can calculate the pressure generated to avoid explosions. It's one practical reason that we would want to know something about the volume use. We use the ideal gas law for stoichiometry problems. The volume is calculated from the moles using PV equals nRT. Now, to solve these gas law problems, first step, convert the known material to moles. Pause this if you need to write this down. If we have a solid, we're going to use molar mass. If we have a gas, we use PV equals nRT. Again, a solid is just like we just finished in our previous chapter. We're going to use the mole ratio next. So 3 steps. Convert what you know to the moles. Use the mole ratio to figure out the unknown. Remember, unknown goes on top. And then we're going to convert to moles again. And then once I have moles, I can go to volume if I know PV equals nRT. Or, like we did in the last chapter, I can go to mass of a solid using the molar mass. You'll have to read the problem to figure out what it wants you to use. So again, looking at our cute little pictures, if I have mass of a substance and I want to go to moles of A, I'm going to use PV equals nRT for a gas. If it's a solid, I'm going to use the molar mass in grams per mole. Once I have moles of A, I go to moles of B. Always use the mole ratio of B over A from the balanced reaction. And once I have moles of B, I can go to volume or to mass, again using PV equals nRT. If I'm trying to find volume, I'm going to use the N that we just solved for from moles of B. That turns into N. And I'm going to put that in my ideal gas law equation. Alright, so we're going to do a quick problem and show you how this works. If I have the following reaction, sodium and water goes to sodium hydroxide plus H2, gas. So how many liters of hydrogen gas will be produced at 280 degrees Kelvin and 96 kilopascals if I start with 1.74 moles of sodium? And I have excess water, which means I don't have to worry about the water. So starting with that many moles, and my conditions that I have, 96.0 kPa equals pressure, 280.0 K equals temperature, and ask me to find volume. In order to find volume, I need to have N before I can find volume. So let's find moles of hydrogen. I know that I have 1.74 moles of Na. I'm already at moles. I'm not going to use molar mass because I'm already at moles, so I don't need to worry about the grams per mole of sodium. I'm just going to worry about going to what I want. I want to find hydrogen, and I know Na. And I apologize, I just put a 2 in front of hydrogen, and it doesn't have a 2 there. So hydrogen is, there's 1 hydrogen for every 2 sodium. So I know that I have, when I calculate it out, 0.87 moles, which is N in my equation. So now I can do the next step and I can figure out my equation. PV equals nRT. And I'm trying to find volume. So I'm going to divide both sides by pressure. Pressure cancels out of there. So volume is going to equal the N, 0.87 moles. R, well, I'm going to look at here. I have it in kilopascals, so I'm going to use the 8.314 kPa per liter per mole K. Temperature is 280, which I know from this. Okay. Divide it by pressure, right here, my 96.0 kPa. So multiply this, 0.87 times 8.314 times 280 divided by 96, and I get 21.1 liters of hydrogen made when I react 1.74 moles of sodium. And that's what the problem's asking me to do. So again, stoichiometry using gases is not that much different than what you just used in the past, in the last chapter. But I sometimes need to combine my PV equals nRT either at this end or at this end, depending what it asks me to find. Now, there's a couple special cases which makes it easier. If you have a reaction that involves gases and only gases, nothing else except gases, then I can use the ratios of the gas volumes will be the same as the mole ratios. Now I could show you mathematically how this works. We could do a problem, work it out with using PV equals nRT and not using it. But the reason behind it is, remember, I'm using PV equals nRT. Over here, I'm using PV equals nRT. So I'm calculating my N. And then over here, I have to go back to using PV equals nRT to calculate my volume. These end up being on opposite sides of the equation, top and bottom. Multiply by it one time, divide by it the next time, and they kind of work out to where they just cancel out. They actually will completely cancel out. So the ratio is the only thing left. The PV equals nRT cancels out on both sides of the thing you have and the thing you're trying to find. So, again, if it's only gases, it doesn't work if there's a solid in there. But if it's gases, if 3 liters of hydrogen react, how much N2 is needed? I can go straight off of my mole ratio is the same as if I had a volume ratio. So there's 1 N2 for every 3 H2. So how much N2 is needed? 1 liter of N2 is needed. How much ammonia will be produced? 3 liters of hydrogen. There's 2 NH3 for every 3 hydrogen. Hydrogen cancel out. I'm left with 2 liters of NH3 are made or produced if I have 3 liters of hydrogen reacting. And that's all we have for this video. In class, we're going to begin doing some more practice problems to make sure you're comfortable using stoichiometry and gas laws on page 442. So you can look ahead at your book for that, and we'll talk about it in the morning. Thanks, bye.